Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome all to today's workshop on TerraMind, Multimodal Foundation Model for Earth Observation Task. My name is Andrea Menara from the ITU, International Telecommunication Union, and it is a real pleasure for me to introduce a new episode in the GeoAI Discovery Series. We launched this series in 2022, and we have been organizing over 40 episodes so far, webinar, hands-on workshops, along with several GeoAI competitions. The current focus on this series is on geospatial large language models and the organization of hands-on workshop, which are focused on building up practical skills in applying AI to geospatial data, under the leadership of the curator of this series, Professor Maria Brovelli. If you missed some episodes of the GeoAI Discovery Series, don't worry. You can watch the recordings of those events on YouTube or on the neural network to which you are connected right now. Without further ado, let me now introduce Professor Maria Brovelli, who will moderate today's event. Welcome, Maria. Maria is a professor of GIS at the Politecnico di Milano at the Geoinformatics Engineering course of study, and member of the School of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst her main activities, Maria is Vice President of the Commission of Geospatial Information of ISPRS, Vice President of the International Society for Digital Earth, and member of the board of the UN Global Geospatial Information Management Academic Network. Welcome, Maria, and the floor is yours.
Thank you, Andrea. So I'm so excited today to present this new geospatial foundation model. Oh, it is not really new, but it's very, very young. So it was published in April, if I'm not wrong, but our speakers can confirm later. So let me tell you something about TerraMind. So it is a model that IBM and ESA's PhilLab developed together. What it makes so special is that it is the very first generative multimodal foundation model designed specifically for Earth observation. Think of it as a model that doesn't just process images or text. It can bring together different types of geospatial data, and it can make sense of it in a coherent way. So it is therefore called Thinking-in-Modalities, where this means that it reasons across different data sources, I can say almost like a human would. And the performance is very impressive because it's already at the top of the charts on key benchmarks that researchers use worldwide. So what we are learning during this seminar is that how to use it. So we will start by talking about foundation models in general very quickly, and then really dig into how TerraMind works. But this webinar won't just be theoretical. We'll actually use a toolkit called TerraTorch to generate examples and to fine-tune the model for a real-world task. So this webinar is meant to be an hands-on, so you'll get to try it out and see how everything comes together. So now, as far as what you need to get started, don't worry, we have kept it simple. So some instructions were already available, and as the minimum, the main thing you need is a good internet connection, a decent internet connection. But if you are connected and able to join us, then you are already all set. The more performant machine you have, the better it is, obviously, but you can join the seminar simply using Colab. Okay, so at this point, as we saw what we are going to do, let me introduce the speakers of today. And I want to start with Valerio Marsocci. Welcome, Valerio. Valerio is
Hi, everyone.
Valerio is an internal research fellow at the ESA Lab, working on geospatial foundation models with a focus on benchmarking them for real-world applications. Valerio received his PhD in data science in 2023. It's finished from the La Sapienza University of Rome. During his PhD, he had the opportunity of visiting the University of Crete and the Institut Géographique National in France. He held a postdoctoral position at CINAM in France and the KU Leuven, Belgium. Then the other two speakers are Benedikt Blumenstiel and Johannes Jakubik. I hope that I pronounce in a correct way your surname, Blumenstiel, correct?
Yes.
Okay, and Johannes Jakubik.
Perfect.
Okay, thank you. So Benedikt and Johannes are AI researchers at the IBM Research Lab in Zurich. As part of the AI for Climate Impact team, they focus on advancing foundation models for Earth observation and have contributed to several state-of-art models, including Prithvi, TerraMind, and others. So I'm very happy to have all of you here today. I'm looking forward to learning how to use TerraMind as the many other people who are connected. And so at this point, the floor is yours. I leave the word to Valerio.
Okay, so hi, everyone. Thanks, Maria. Thanks, Andrea, for having us here. Basically, yeah, today we're going to talk about TerraMind. So we're going to tell you something from a technical point of view, and then we're going to show you on hands-on. Just to go a little fast, but to show you the agenda, we are going to see that in the first part, I'm telling you some technical details about TerraMind because it's also nice to understand why it's working that well. And then there will be also a short introduction about TerraTorch and how then we are going to go through a lot of tasks in which you can learn how to use TerraTorch and TerraMind all together. And then, of course, there will be at the end we have a Q&A moment, but if you have some other question, you can drop in the chat or at any moment, of course. Starting introducing a foundation model, so TerraMind and why TerraMind is working and what are foundation models. Basically, as you know for sure, every day there are tons of data that are produced. And if you just think about, for example, Sentinel-2 satellites, there are up to 3.5 6.2 terabytes per day that are produced. And these basically are representing how our work works, how we can monitor a lot of different downstream tasks with this kind of data. And this means that these data themselves can be then the starting point to pre-train foundation model. So of course, now the question can be, what is a foundation model? Basically, a foundation model is a deep learning model that with this very same model, we can solve a lot of different downstream tasks. So using the same backbone, so the same feature that we learned on all the data that we mentioned, for example, before, we can have different downstream application. And downstream application, of course, when we say downstream application, we refer to different tasks, both from a technical point of view, so computer vision point of view, but not only, but also like application, like real world application. If we want to focus on the tasks, in this slide, we just reported 3 tasks, for example, semantic segmentation. So given one input image, we can have a map in output in which to each pixel we are assigning an information. And this could be mapping some disasters like wildfires, floods, and so on. We can have some classification task in which we have given one image in input, we can have one label for the whole patch, for the whole image. And this could be any kind of task. That could be land cover, even floods or no flood, but other tasks could be forest monitoring, habitat monitoring, and so on. And finally, when we want to infer for either a single patch or a single pixel, continuous value. So that could be the height, could be the temperature, and so on. We have a regression task. And two examples that I just mentioned are literally this. So basically urban heat, in which we are inferring the temperature, and for example, the biomass, in which we are inferring the height of the trees, we can say. But if we want then to focus on other tasks that are around when we're talking about foundation model, well, there are a lot of applications, and this application have different domains. And in the next slide, we have just some of them. So for example, in this, we can see that we have a lot of tasks that are related to different risks and different relevant topics to date. So for climate risk, we already mentioned some of them, like flood mapping and so on. But we have also any other kind of emission that could be climate related, weather related, and also for some other tasks that these days, unfortunately, are more and more relevant, like intelligence. At least the one that are about ship tracking and so on. Maybe it's unfortunate that they're getting more and more relevant. But okay, basically now we understand more or less how a foundation model work, why a foundation model can work well, and when it can work well. So now we can go on and talk about our foundation model, so TerraMind. TerraMind, as Professor Saborelli already mentioned, was developed by IBM and ISA and is groundbreaking because it put together a generative model. So basically a model can generate images from one modality to the other, so an any-to-any generation model with a very strong discriminative model. So the same model, the same foundation model can solve both the task, generative task and discriminative task. How can it do it? Basically with the cross-modal understanding. So basically having one modality, the model is basically having an input a lot of modalities, and we're going to see which of them are around and so on. Understanding how these two modalities interact and which is the correlation between these modalities, among these modalities, then the model itself can learn good features that can solve different downstream tasks. And we will see also which are the different tasks that TerraMind can solve and so on. If we want to focus on an example, so an easy example, and then we go on into details. So don't worry if you are craving some deep learning algorithm details. But if you want to focus on an easy example, we can imagine, for example, a Sentinel-2 image. So we have a Sentinel-2 scene. And in this scene, for example, we have a lot of clouds. Imagine a downstream task in which we have a lot of clouds. So for example, flood mapping, there's just been a flood, and we want to have, of course, some info about it. What if we can just rely on Sentinel-1? So basically we have a Sentinel-2 with a lot of clouds, and we want to infer some info about it. We can use the Sentinel-1. So for example, instead of these images, we can have the images in the image in the next slide, in which we have the Sentinel-1 image that is on the very same area. So thanks to TerraMind, TerraMind works learning the correlation between the Sentinel-1 modality and the Sentinel-2 modality. How why this? So that if we, for example, in this case, for the Sentinel-2, we have some areas that are covered, we can use the Sentinel-1 image either to solve, for example, to generate the correspondent Sentinel-2, or just learning the correspondences, the consistencies, solving the task itself, just relying on the Sentinel-1. So if we want, for example, to see them overlapped, we can see them in this nice example. And in this way, we can have all the most of the information that we could have on the original one, also just relying on the Sentinel-1. But now, given this, we can go on the model itself. So basically, the TerraMind model works, as I told you, works both on generative task and discriminative task. And it was pre-trained on 500 billion tokens, using a lot of modalities that are the one that you can see on the first column of the slide. So basically, Sentinel-2, Sentinel-1, DEM, and DY, land use and cover, but also other sequences. So some data that are sequences. As you can see, we have the first part of data that are treated as images, and the other one that are treated as sequences. To do so, then TerraMind basically is using a, let's say, two-step pre-training strategy. In the first one, given that we observed that it could be a very good input for our encoder-decoder architecture, that is the one that you can see on the right part of our slide. So the encoder-decoder architecture, given that we observed that could be very nice to input in this encoder-decoder architecture, not just pixel like it happens generally, but also tokens. There are basically two steps of pre-training. The first one is about a tokenization step, and then the other one is about the encoder-decoder step. If we want to focus on the token, on the tokenization, as you can see, we have an image tokenization and a text tokenization. For the text tokenization, we're just using some tokenizers that are already very widespread in the literature. For the image tokenization, we're using some cool technique that is basically based on an autoencoder. So basically, in this autoencoder, we once again, just to be very clear, we observe that using not just pixels but also token is leading to better results. So for this, we are using pixel like always, and then tokens. For the tokens, in the next slide, we are showing you how this tokenizer is organized. The tokenizer for the image level, for the image modalities. Basically, we have an autoencoder. This autoencoder is extracting some from each patch of our image, is extracting some tokens themselves that through finite scalar quantization, and with a codebook that has a size of almost 16K tokens, 15K and 360 tokens. Basically, we encode all these patches from our image with some finite tokens. Then, as a decoder of our autoencoder, we have a diffusion decoder. And this is very nice because we have also in this case a diffusion part that will be very, very fruitful. We will see in the generation part. So in this case, as you can see, we can encode in a finite way, in a discrete way, the patch from our image. And then we can provide these tokens in the input of our encoder-decoder architecture. So then basically, in this way, in the encoder-decoder architecture of TerraMind, so basically in the slide that you can see, in which we have different modalities in input. So in the next slide, we have, for example, 4 modalities in input. And as you can see at the center, at bottom center of our slide, we have as input both the pixel level input, the small patches that you can see, and the token level input. So, and this can come both from different modalities and same modalities. Why this? Because we want to, once again, to better understand, for example, the correlation both among different modalities. So for example, in the images, you can see that we have Sentinel-2, Sentinel-1, we have land use, land cover, and some coordinates, but also within the same modality, if we're combining pixel level inputs, so the patches that are projected through a patch embedder with tokens, we can also encourage the machine to learn this correlation within the same modality, but given into different representation of it. So one is discrete and one is continuous. Basically, after having this sampled input tokens and pixel level that then are projected in tokens through the patch embedder, we encode this in latent representation. Then, thanks to a masking strategy, very easy masking strategy, and our decoder, once again, with a cross entropy loss, we want to enforce the correlation cross modalities. So basically, given some tokens of one modality, we want to infer the tokens from the other modality. In this way, then the TerraMind algorithm is working, and the TerraMind is performing that well. If we go back to the again to the whole picture of TerraMind, so in this slide you can see that basically, okay, once again, given our input modalities, we can have pixel level input that are projected to a patch embedder and token level input. So basically the same modalities go through our tokenizers, and then all these tokens, so both the images tokens and the tokens that were already tokenized, we have an encoder decoder architecture based on correlation learning, so cross entropy across modalities. With this strategy, then we can have basically 3 downstream applications that are multimodal generation, fine-tuning, and thinking in modalities. We're going to see the 3 of them, starting with the multimodal generation. That we can call any to any generation, because given one modality, we can basically go to any other modalities among the one on which we pre-trained our TerraMind. How it works? Kind of easily. So basically, we have an input, and we make it in in patches. These patches go through the TerraMind encoder. So we have then some latent representation of this. With this latent representation, then of course we have the target modality. So imagine that we have a Sentinel-2 images, and we want to we want to generate a Sentinel-1 images. So basically, we have the representation of the Sentinel-2 images, and with this, we want to infer the features, so the tokens of the Sentinel-1 through our decoder. Once we have these predicted tokens, so the inferred token. Yes.
Valerio, sorry for jumping.
Yeah.
I saw that there are couple of questions, and I believe that one is very relevant for the people for understanding. There is Fuat Ins who asks, please explain what a token is. Give some examples. Then when you finish speaking, I will ask also another question, but this is very relevant because if people don't understand what is a token, it's difficult to understand everything here.
Okay, no, basically, if we want to talk generally about tokens, let's say that a token is just a representation of a part of our image, basically. So basically, we have our image, like you can see in this row input, the image in the row input, and imagine that we are dividing the image in patches, in small patches that in this case are 16 per 16. So there is a window, sliding window, let's say, that is going on our images, extracting all the small patches. Each of these patches are then going through our transformer that is learning some feature. The feature that represent this patch are literally a token. Then this token can have different shapes, can be of different length, different, could be, let's say, whatever, but is just a representation of the patch size in input, of the patch in input, sorry. In the case of, in the case of this slide, so of the tokenizer itself, then these tokens are just through the vector quantized variation autoencoder. Basically, these tokens are just discrete numbers that are representing the input patch. And through this code book that has a fixed number of tokens, let's say that the code book is a bag of features. So it's a set of features that is already there. And the tokens representing the patch is basically a combination of these tokens that are fixed in our code book. But if we're talking more in general about what a token is, because tokens come also to the other slide. So if we go back, for example, to if we go back to the big picture of all TerraMind, that was a few slides after. In this you can see also that we can refer to tokens also when we refer to again pixel level input go through the patch embedder, and also in this case the patch embedder is just projecting the input patch into this feature space. Also in that case we can talk about a token. So basically the token is just a representation of our patch, of our image, of a part of our image. So I hope that this answered the question. But then going on with but if it's not clear, of course drop again another question and we can discuss about it, because I think it's kind of relevant to discuss this before we go on.
I believe,
but then if we go on
Valeria, I believe that it could be easier to probably to make an example with the text, saying that with the text, the token can be one word or one part of the word. And this is exactly the same. So it's one part of the image, this token we are speaking about.
Yes, then generally reprojected in the feature space. Yeah.
Okay, but
In
the
this case, when we
starting
talk about
point,
tokens, in
the
this case,
starting point is that we consider parts of our image, and the one portion that you say one patch, you call it patch. This patch is our token, or we transform it in such a way to be our token.
Yeah. Okay, thanks a lot. So then we're talking about generation. So basically, again, in this case, we produce some token with the encoder, and then we predict with this token that are the tokens that represent our input modality. We predict the tokens of the output modality, so the modality we want to generate. And then, of course, with the tokens that we have predicted, we apply this diffusion decoder. So basically, we have a diffusion that is going from tokens to the images that work thanks to our first pre-training step, that is one that we showed you before. But this is just if we want to go from one modality to another modality, going through a change generation. How it works? Basically, imagine once again that we want to go not from Sentinel-2 to Sentinel-1, but to Sentinel-2 to DEM. And in the slide before, we observed that with Sentinel-2, we can produce the tokens of Sentinel-1. So basically, a representation of our images. So the tokens again are this part of the images that are represented. So basically, we have this image, the Sentinel-1 image that is encoding in these tokens. So basically we have information not just about the Sentinel-2 modality, but also about the Sentinel-1 modality. In one case, we have pixel level input, as you can see, the second column, let's say, of the image at the bottom. So we have the input, pixel level input for our Sentinel-2, and then we have the red tokens, the target token that are representing Sentinel-1. Thanks to the TerraMind architecture, we can input in the encoder both, so that the predicted tokens for the DEM, that are the green one, are taking into account information not just on the Sentinel-2, but also on the Sentinel-1. In this case, then the predicted token should be, let's say, better, should be more refined. And in this case, then we can once again diffuse our tokens and have a final image. Then and why this is helpful? Of course, this is helpful because it helps to have consistent generation, because in this case, of course, the generated images should correlate not just with the input one, but also with the intermediate steps. Then if we go on with Thinking-in-Modalities, so one of the other tasks, there were three, generation, Thinking-in-Modalities, and fine-tuning, general fine-tuning. With Thinking-in-Modalities, what happens is similar to what we already to what is already existing, to what we already discussed, sorry. So basically, we have an input image, and instead of directly inputting into the encoder decoder architecture, in which the decoder is the decoder for our downstream task, like in this case it is just a semantic segmentation head, With TerraMind, we generate also some tokens on an intermediate modality. So basically, in this case, we have sentient twin input, and instead of just solving the task, so in this case, binary segmentation, we generate the tokens for land use and land cover. Why this? Because of course, if we generate some information about land use and land cover, this can help us, land use and land cover map help us better in solving the binary classification task, in which in this case, for example, we want to have water bodies segmentation. And then with the tokens from the auxiliary modality and the input image, we can then put both of them in the model and solve our task once again. And this can be done, of course, with one modality helping, but also other modalities. And of course, this was named Thinking-in-Modalities because the machine can help itself thinking, going, through different modalities, so gathering info from different modalities. Going very fast on the third task, we want also now to understand how does TerraMind perform. So basically, okay, it's very cool. It makes a lot of sense from an algorithmic point of view. It looks like it's working. The generation are very looks very similar to reality. But how does it work? Basically, we benchmarked it on Pangea, that is one of the most widespread benchmarks that are developed. And there are different tasks. We selected then nine diverse downstream tasks, in which we have, as you can see, different modalities. So we have Sentinel-1, Sentinel-2, planet data, high resolution data, RGB, SAR. So we have a lot of modalities, and we have also a lot of tasks because we have change detection, semantic segmentation, binary segmentation, and different domains, because for example we have disaster mapping, we have marine environment, and so on. And if we want to see some results, basically we benchmarked it against many foundation models, and we see that in average it is the best. And also if we check the single tasks, most of the times it is the best. So if we have an average rank of it, basically it is the best among all these results. You can see in this slide in particular that the blue line is both the dotted one and the full one are the one referring to TerraMind, and the TerraMind V1 large is getting the best results on most of the tasks. And when it's not the best, it's second or third best generally. And we were also very happy to check about the multimodality. So, okay, we discussed a lot about multimodality, about the representation and so on, but is this true also in the real world tasks? Well, the answer is yes. In fact, there are mainly 3 data that are completely multimodal in the Pangea. That are pastis, so agriculture, and one flood that is about flood mapping, and CTM that is once again agriculture. And we observe that if using just one of the 2 modality, the results are always worse than when using both. And this is true both for easy datasets like Sen1 floods and very difficult datasets like, for example, pastis and the other, and both for single temporal and multi-temporal datasets. So this also is very, interesting because it means that it is very cool, not just from a architectural point of view, but also from results-wise point of view. And yeah, that's all for the introduction from the technical point of view about TerraMind. I don't know if there are other questions you want me to answer now. Otherwise,
Yes, there are some questions, Valerio. So I will start with, there's one question that I will leave later to Benedikt and Johannes, but another question is, why is it beneficial to discretize the feature space through tokenization?
Okay, so basically the main idea is that, as I told you before, given that the model is where we want to force the correlation learning, so basically to understand how, let's say, how different feature can be, how we can infer some information having some set of feature with respect to others. If we, in this case, we thought that having the same modality, so within the same modality, having the same modality encoded in 2 different ways. So in one case, on the pixel level, so just with Apache embedder, and in another case with the tokenizer that we showed you, this could really enforce the model to find this correlation between these 2 modalities. So to find, let's say, the most salient feature that are really representing the modality itself independently from if they are learned in a discrete way with the tokenizer or in a continuous way through a patch embedder on the pixel level. So basically, this is the idea, to have the same modality represented in two different ways to understand which are the most salient features that are really useful for the downstream task for the rest of the pre-training.
Okay, and this was a question by Luc Vermeer. I see that there is another question by Luc Vermeer, so I ask also the second one, and then I switch to two other questions. Oh, a lot of questions. So, second by Luc Vermeer is, why does TerraMind B outperform TerraMind L on some tasks? Were they trained on different data?
Okay, no, they were trained on the same data, so they basically also especially the protocol for the downstream tasks on the fine-tuning step where was totally the same. So the steps were the same, but generally, I mean, TerraMind B, of course, is base and L is large. So the question is like, why a bigger model is working worse than a smaller model? This can happen because of different factors that are very connected to some datasets. So, for example, there are some of the datasets in the Pangea bench that are kind of small. So it could be easier to that a very big model is not saturating, so it's not learning enough, let's say, on this very small model. Or on the other way, there could be a smaller model like the TerraMind B can like some sort of overfit on some dataset with respect to the large. So basically, these are the two main reasons.
Okay, thank you. Very clear. And I have three more questions. I'm not going to accept any other questions by now. So in case there will be more, they will be answered at the end of the hands-on. So Moti Gupta asked, in contrast with multimodal Earth, you are using tokenized embeddings. Do you see better performance with tokens? Does it objectively do better or does better in less compute? What is the benefit over diffusion encoder over the coders used in AE, since diffusion models are more for visual texture, but for SSL, we need a better semantic? Oh, it's very long. It's a very long. I don't know if
Okay.
you want to answer now or if you want to answer later.
Let's say that I can give a general answer, and then if there is some more stuff to discuss, we can discuss it later. But basically,
Yes.
So about the last point, that's true, but it's not totally true in the sense that it's not true that diffusion are just for visual. And there are some recent paper, both from let's say computer vision in general and from Earth observation, in which I'm part of one of these paper. Okay, so for this I'm mentioning as well, but in which we are showing also that the feature in a diffusion model are very, very fruitful also for to have better semantics. So for example, we tried this with the diffusion sat, and it's basically working, is one of the best. If you just put some fusing strategy to use the feature in diffusion sat, is getting very, very good performances on all the geobench tasks. So on this, using also some diffusion techniques can help in this. It can help also in having better semantics. And then in the case of TerraMind, we wanted to have both a discriminative model but also a generative model. So this is also the reason why. And about what else? I think that for now this can answer.
The Earth.
Okay, on MMEarth, I can tell you that is we're. I mean, in the next months, like I would say January probably, we're gonna have also all the results about MMEarth on Pangea, because we're working on this, adding a lot of new models on Pangea. Because I'm part of basically of the Pangea benchmark. So we will get back to you with all these results, and we can really say MMEarth is better, not better, and we can understand why it's better, not better. But I mean, I have the feeling that TerraMind, I mean, is doing well. So let's see.
Okay. The other question by Moti Gupta was a question by Moti Gupta. The previous one is in Thinking-in-Modalities, which network is used for generating the synthetic modality? Is it the TerraMind encoder or decoder or something else?
The encoder.
Okay, this was very
We are
quick.
using the
So
encoder. Yeah.
last question, and then I will ask you the other. There are other questions, but I will ask in the end. But the last question I'm asking now is by Pretimoy Potter. Is it possible to utilize TerraMind to synthesize a cloud-free view of an area from a single heavily clouded Sentinel-2 image while ensuring the resulting output accurately represent the temporal characteristic of the original acquisition date? Yeah.
You will find out later. You will find out. I mean, you will show us if this is possible. Basically, no. I mean, theoretically, it should work. But now, all these tasks, because there are so many tasks, we are benchmarking them step by step. And on some of them, it's already performing greatly. On some others, we are making it. I mean, we want really to understand at which level we are. But this specifically, from my side, I have no precise answer. I don't know if then maybe Benedikt and Johannes want to tell you something later. But yeah.
Okay, so let us see if Benedikt and Johannes can add something more later. There are two other questions, but I will leave them for the end, giving the word on the opposite to Benedikt and Johannes in such a way that they can start showing us also the magic of TerraMind. So many questions, guys, so many questions. Good. It means that there is a great attention and expectation with respect to this TerraMind. So thank you so much, Valerio. It was so clear, was so nice, and so now I believe you will stay here with us. But let us give the word to Johannes and Benedikt for better understanding how to work with the TerraMind.
Cool. Thank you so much, Maria. And also thank you so much, Valerio, for this nice presentation on TerraMind. Maybe just connecting to the last question on cloud gap imputation. I think one thing that we can show you on that is this is a Sentinel-2 tile, right? So you see some cloud coverage here. And this is the generation of TerraMind for the same Sentinel-1 image. This is completely generated. This is an artificial image derived from that. And if we put them next to each other, you can kind of see that the semantics make sense, but obviously, and I think this is something very important that this question is bringing up. I mean, TerraMind cannot infer magic in the sense of if there's something happening on this optical satellite image that is cloud covered, say, you have a huge birthday party in a park that is visible from a satellite, then this will obviously, if there's cloud coverage, not be able to infer from TerraMind's perspective. So you will not be able to make up information that you cannot infer from the context. But what TerraMind will give you is something like the average representation of what it's expecting underneath the cloud. And the same applies to shadows. So don't expect that TerraMind can infer something from a cloudy image that is just impossible to get as an information, but expect that TerraMind will be really good in generating an image that represents the average state of that area in that specific region at that specific time. Okay, with that, let's go on and talk about how you can work with TerraMind. I guess that's hopefully a reason why you're all here and listening to this webinar. So basically for us, both in ESA PhyLab and IBM Research, it's really important to make sure that people can use our models. So all the models and the associated code is open sourced under Apache 2.0 license. You can work with these models under very permissive license. they're all on Hugging Face in the same organization called IBM Geospatial. You will find the model itself, the tokenizers that are used for deriving these quantized tokens that we've been discussing about, and everything you need in terms of interacting with the models. And a big component of interacting with models like TerraMind in general is TerraTorch. TerraTorch is much more than your door to TerraMind. It's also your door to any other model that is integrated within TerraTorch. So effectively what TerraTorch does is it's a toolkit to very simply interact with different foundation models with different other pre-trained backbones to apply them to downstream applications that you're interested in. So this allows you to easily do fine-tuning, thinking in modalities, generation, and all of that. And you can see on the lower left how easy it is to instantiate those different models. In that example, it's TerraMind base with 2 different modalities as input. You just need these 2 lines and then you will have the model available. And I will tell you a bit more on how this works and also why we do this, what's our motivation with all of that. So I think the most important thing is everyone who is familiar with PyTorch Lightning will understand that TerraTorch is just a wrapper around PyTorch Lightning. For everyone who has no idea what PyTorch Lightning is, I will explain a bit in more detail what is going on. Let's start from bottom and go to the top of this image. So we said you probably want to interact with some different models. Hopefully TerraMind is one of them, maybe Prithvi is another one, maybe Clay is another one, maybe, yeah, there are so many backbones right now that you can choose from. So those are the models that you're interested in. Then, depending on your downstream task, you want to choose an associated head, a decoder. So effectively what you do is for a segmentation task, you might choose a UNet decoder or a UPNet decoder. For other tasks like classification, it might be something simpler. Effectively, the idea is that your backbone, TerraMind, for example, extracts features for you, and then your decoder takes over and transforms these latent representations into something like a segmentation mask or a class representation. And on the left side, we have the data perspective. So there we have different types of dataset classes that we support. Obviously, there's the opportunity to customize something. So this is for people that want to apply one of these models to their own datasets. But we also support the Torch Geo datasets and a couple of other more generic dataset classes that are directly integrated in TerraTorch. And then there are a couple of different splits. So everyone from the deep learning community will recognize them like train split, val split, test split to train your model. And all this is wrapped within TerraTorch's data modules and datasets. So on the left side, we are done with preparing our dataset for a specific downstream application. Say, for example, for flood segmentation, we now have a dataset class and a data module, and those individual splits defined. On the right side, we choose a backbone. We will later choose TerraMind with some of these decoders. In our case, it will be UNet decoder. And then we will have to tell TerraTorch what task to perform. It can be segmentation, it can be pixel-wise regression, classification. Valerio nicely introduced them in the beginning, so you can now choose from them and then hand everything over to PyTorch Lightning, which then does the magic of the fine-tuning process. And everything that I just explained is very, very lightweight in a sense. So you either do that through a config in a no-code environment or in a low-code environment. And I will show you how to do that in a second. So I think one thing that people generally struggle with understanding, and therefore we spent one extra slide on that, is how this encoder-decoder factory works. Encoder-decoder factory, it's really like that. It's a factory that glues together different encoders with different decoders to your downstream application. So for the backbone, we just said there are different backbones, right? One of them is TerraMind. And basically what the backbone does is it goes from the input images to some features that it extracts from them. And then we have something called a neg. A neg just reshapes the encoder output so that it's compatible with the decoder. And the decoder then facilitates this mapping to, for example, a segmentation mask. And ultimately, a head will predict the final target. And the cool thing is, once you define all of that, then, as I already mentioned, you can either use low-code environments, and I will show you in a collab how this works, or even no-code. I prefer the no-code environment, to be honest, because I work more in pre-training, so I work more in the pre-training of TerraMind and other models. And I'm using TerraTorch to understand how well these models then perform during pre-training. So this no-code environment allows me to just use a config where I pre-configure which backbone I want to use. In that case, it's a Prithvi backbone, which bands I want to use, and so on. So I specify all of that once, and then I have that config, or I just take it from the TerraTorch Git repository or from other Git repositories, and then I just run a single line of like a single command, and TerraTorch will take care of the rest. So yeah, with that, I will switch in a second to actual code and show you how this works. One little announcement for the second half of this webinar. I will show you how to fine-tune TerraMind on flood mapping, but we want you to take something back home. So after I show you how to do it with flood mapping, we invite you to try it yourself and try to adapt this as far as you can take it for a burn scars task. And there's a new notebook for this that we prepared dedicated for this session that you will find in our Git repository. We will show it to you in a second. If you want to participate, there will be a 10-minute break within this webinar where you can get your hands dirty and engage with this. And after this 10 minutes break, we will go through step by step on how to adapt these configs so that afterwards, hopefully you have a good idea on how to use TerraTorch and fine-tune models like TerraMind. Perfect. With that, let's go to the code and make our hands dirty. Yeah. Oh, yeah. Good call. Okay. For everyone who has never seen the TerraMind Git repository, so if you Google TerraMind, probably the first thing that will pop up is the Git repository with a lot of information on how to use TerraMind. And there are a couple of different links to notebooks. We will use the Sen1 Floods 11 notebook, and there's also the collab associated to it. And then as another thing, there is this newly prepared burn scar notebook that you can make yourself, and also a collab associated to it. So when you click on the burn scars notebook, then what you will find is something like this. And what we prepared here is a notebook with a couple of to-dos. So you can see within the config what we ask you to do to go from the flood mapping example to a burn scars example. And then we will later go through it and show you what our best approach to this would be. And
Sorry, Johannes, for jumping. I see that yeah, there is one person asking to share the collab link. But I believe that the collab link has already been shared in the neural network. Correct, Pauline?
Actually, Benedikt just also shared the link to the repository, and there you can find all the links.
Anyway, in the neural network, you can find already shared the collab link. So please, Roman Taufik, go there and you will see the link. in such a way that you can work together with us.
Cool. Perfect. That's an important point. And then finally, what's also important, there's also a link here within the first paragraph of TerraMind as a repository that brings you to the documentation of TerraTorch related to TerraMind, but also all the other versions. And people like Benedikt do an amazing job in describing how to use the models, what's available. So you can click through that. And all of your questions that you will have on your first day are very likely to be answered in this document. On your second day, maybe you have a couple of questions that you want to talk to us about, but on your first day, I'm pretty sure that this will cover most of your questions. So please feel free to have a look at the TerraTorch docs, especially for TerraMind. There's a lot of very good content. Perfect. Now, as a next step, we will go to the collab of Sen1 Floods 11. And the first thing that we want to do here is we want to change the runtime to T4, just to make sure that afterwards all participants or none of the participants get a huge bill from Colab, but we're also not stuck to a CPU. And then the first thing that we do is we install TerraTorch and a couple of other packages. This will take a second, and after the install, you always have to restart the kernel of Colab. This is a normal thing. It also applies to Jupyter Notebook. So the moment you install new stuff, you have to restart your session to make sure that the changes take effect. So this is what we will do now. Obviously, if you run this like on your local laptop, obviously you do that once. So we will just show it to you in case you have never done it. And then we import everything. So there are a couple of packages that we need on top of TerraTorch. For example, Torch itself, and a couple of others. While this is still loading, if there are any questions and if you cannot find the right links or anything, then please let us know in the chat so that in the back we can share these links with you again.
While we are waiting, one question is if the slides will be available. So it refers to Valerio. I believe yes, that slides will be available, but I'm asking confirmation to Valerio in such a way that we can put the slides on the website together with the video and everything. You are muted, Valerio.
Yeah, they will be.
Okay, thank you. Thank you so much.
And actually, if you're interested in different versions of this talk, there will be a couple of other YouTube recordings and a couple of other slide decks, so you can see the evolution of the slide deck, basically. All right, cool. While we were discussing about the slides, we already downloaded the data set from Google Drive. So this is like taking care of it within this cell. So we now have the flood data. It's roughly 2 gigabytes of flood data downloaded to our Colab. And we will also download TerraMind Tiny and TerraMind Small. We will download associated configs that we pre-configured that everyone can use. There are a lot of configs available already in TerraTorch, and we will go through them afterwards in a second. What I want to show you right now is the moment you have your model and the moment you have a config available, and again, for many tasks you already do, only, of course, not for your custom applications that you might be interested in, but for a lot of relevant applications, those are available, then using the model is really just a single line of code. So you call TerraTorch, which is, again, the package that helps us to fine-tune all of these different backbones. You specify that you want to fit a model, which is lingo for fine-tuning a model. Then you specify a link to your config. In our case, that config has the name TerraMind tiny 71 floods 11. And then you see something like this. Some magic happens and TerraTorch starts its process where it first summarizes what it will basically do. So there's a model which is a pixel-wise model because we want to do pixel-wise segmentation. We have roughly 8.4 million parameters that are all in train mode. Our criterion, which means our loss function, is a dice loss in that case. And then there are a couple of different metrics that we are logging. And then TerraTorch starts its process with a quick sanity check where it makes sure that the data loading works appropriately. And if this is confirmed, then you see that basically TerraTorch starts with fine-tuning the first epoch. Obviously, we don't want to wait now for 100 epochs. So I will quickly jump over that. But if you want to know what happens after 100 epochs, you can just go through that or load some existing checkpoints. What I want to do as a next step is I just showed you that everything can be a single liner, but we have not talked at all about what happens in like under the hood, what happens in this magic, right? So we just so far learned that if I have a config and if I know which model I want to use, then I can just call TerraTorch fit on that config, and then TerraTorch will take care of everything. What I will show you now is what actually happens under the hood to get just a better understanding of TerraTorch itself. So the first thing is we will inspect the data. So within this Zen 1 floods 11 dataset, there are a couple of different subdirectories. So there's a hand-labeled set of data. Then you have some Sentinel-2 tiles, you have some Sentinel-1 tiles. This is what Valerio was referring to before when he said that this is a multimodal data set. So there's optical data and radar data in there. There's annotated data, weakly labeled data, and so on. The structure looks roughly like this. So we always have the location, and we have an identifier. Then the name, like the file name, specifies whether it's optical data and whether it's hand labeled or not, or if it's radar data. And then we see that it's a TIFF file, so we need something like a TIFF loading for that. And as a next step, we need a data module. What a data module basically does is it specifies what kind of modalities, what kind of data goes later into the data loader, and everything related to that, everything related basically to the creation of the data loader. So in that case, we said we will perform a segmentation task. We will basically, we try to map the outline of flooded areas. A batch size basically specifies how many images are put forward to the GPU at once. The number of workers specifies how many CPU processors are doing that job of data loading at the same time. And then number of classes, in our case, it's a binary problem. Areas are either flooded or they are non-flooded in this scenario. We then specify which modalities we want to input. In our data set, we have both Sentinel-2 and Sentinel-1 data. So we will make use of both of them. And the modality that we will use as the RGB modality is the RGB bands of the Sentinel-2 data, right? All right, then we need to specify the path to the training data, to the validation data, and to the test data. And we already saw that the structure of the data set is something like this. It's first which satellite it is, and then whether it's hand labeled or not. So this is what you see here for Sentinel-2, for Sentinel-1, and then for the label. And this is the same across training, validation, and test for that data set. So this is good. As a next step, and this is also something that we had in the slides, we need to specify what kind of splits we want. So for everyone who is not so familiar with the concept of splits, we use splits in deep learning because we need to get an understanding of how models perform on unseen data. So the unseen data, the holdout data, this is the test split. So here we specify which instances of the data are completely unseen and will not be touched by the model during the fine-tuning process. The train data is obviously the opposite. So those are all the instances that are fed to the model so that the model can adjust the weights for this task. And then a validation data set is so that during our fine-tuning process, we can validate how well our model is doing and monitor the training, see whether the model, for example, overfits. And this is kept separately to make sure that the test data is still uncontaminated. Great. Then we tell basically TerraTorch about how to identify the correct instances. This is what a grep does. For everyone who is familiar with Linux, in Linux, a grep allows you, like within a directory, to get the instances that have a specific pattern. And in our case, the pattern is that for Sentinel-1 data, we want them to have a suffix that is Sentinel-2 hand.tif. For Sentinel-1, it's similar, but Sentinel-1 instead of Sentinel-2. And for label, it's label hand.tif, right? We also tell TerraTorch which bands it should leverage. For example, in Sentinel-1, there are a couple of different bands, right? But in our case, we use VV and VH polarization, both as dataset and output bands. One very important step for any kind of deep learning, and I feel like if fine-tunings fail, in at least 60% of the cases, they fail because there's something wrong with how the data is normalized between pre-training and fine-tuning. So be very careful and very mindful of how you apply these means and standard deviations. As a side note, there's also tooling in TerraTorch that allows you to derive these means and standard deviations with a function that's called compute statistics, but that's just a side note and nothing that we will cover today. So we pre-computed all of these means for the different modalities, and we use them to basically standardize our flood input data so that there's no distribution shift for TerraMind between like what it has seen in pre-training and what it now sees in fine-tuning. And finally, we apply a set of transformations. There are a couple of very successful transformations in a package called albumentations, and TerraTorch often draws on them. You can define custom ones, but my understanding is if you use albumentations D4, which exhibits a couple of rotations and random flips, then you're already pretty good. And then you want to make sure that everything is transformed to a tensor so that the model can deal with it. Obviously, we will not perform any transformation on the validation or the test data, just on the training data to make our data set a bit larger and a bit more generalizable. All right, there's also no label replace and no data replace. Imagine you have non-labels, for example, in your data. Happens to Earth observation people a lot of times due to swath, due to cloud contamination. In these cases, we can specify what non-values should be mapped to, which is quite convenient. Perfect. We execute this cell, and in the next step, we will see that we get a data set from it. So this is as simple as that. In that case, we are looking at the validation data set, and we see that we have roughly 90 images in the validation data set. Here's a helper function for plotting, and we will do exactly this. We will plot the data that we will now put into TerraMind as a training data set. So I hope so far it was not too dry. What I was trying to convey as a message is there are a lot of things that we specify in the background that are just related to how your data looks like, and this is very customizable so that you can use it with your data. But then once you have that config, then building something like a data set, like a data loader is super easy. And we take care of a lot of the heavy lifting for you with TerraTorch. Okay, now that we had a look on the data and we kind of see where there's permanent water, where there's flooding, where there's cloud masks and background, we can obviously do the same for the test set. So we can also check on that. It's pretty much the same thing. We have 90 images there. We will not visualize them once again because you get the concept, but just as a sanity check, right? And then we need a second component, obviously, which is the model. So far, we just focus on the data side. Now I will show you what happens under the hood for the first thing is in TerraTorch, there's something called a registry. I think people that are not computer scientists often struggle with the concept of a registry, so I will try to explain it briefly before we start over and load TerraMind. Basically, in a registry, we specify different versions of models. So the registry, as the name suggests, registers different versions of a model. For example, in TerraMind, that's tiny, small, base, and large. And with that information, TerraTorch always can look up based on these identifiers like TerraMind v1 small. It would know, oh, I have to look up in the backbone registry where I can find more details on how this model is actually built. And it will grab everything it needs. It will grab the associated checkpoint with the weights inside, and it will make sure that the model is loaded appropriately afterwards. So this is a registry, and there are different types of registry in TerraTorch. I think it would be a bit too far of a stretch to cover all of them, but what's important is that there's a registry for the backbone, which is where TerraMind lies, which is where other models lie. Then there's also a decoder registry where stuff like unit decoders, UPNet decoders, and so on are. And basically, you can also have a look on what's actually in there. So if you run this cell, then you will see we are here looping over the TerraTorch backbone registry for all models that have TerraMind in their name. And you see that there's TerraMind base with Thinking-in-Modalities, large, and so on, right? You get the concept. And also all the tokenizers will be available there. Perfect. We can do a similar thing for the decoders. So if you want to get an understanding what decoders are available, we have, for example, a SAT-MEE head. We have a UNet decoder. There are a couple of different things that you can make use of. In our experience, UNet decoders perform pretty well for segmentation tasks. So this is our go-to, and this is also what we will leverage here. And then, as I said before, using TerraTorch to build the model is pretty easy because TerraTorch has this registry, right? And we already discussed what that means. So it has kind of a lookup on how to build the model. And then we just call the build function for a specific model backbone. In that case, it's TerraMind v1 small. We say it shall be pre-trained, so TerraTorch will load the weights automatically. And there are the modalities that we want to use. So TerraTorch will automatically build the input adapters for Sentinel-2 and Sentinel-1. So if we execute this cell, then you will see that the TerraMind checkpoint is downloaded from Hugging Face. For small, that's quite quick. The model will be built and everything is executed within 6 seconds. We can now have a look at the model. It's a much less intuitive representation of the model compared to our slides, hopefully, but basically it's pretty much the same thing. So you will see that we have these input adapters for Sentinel-2, the optical data, and Sentinel-1, the radar data. You see that we have an encoder in here. You will see that this is the different transformer blocks. And then here are some connectors, let's say, that we can later apply to either the NEC or a decoder. So what we will have, or what we will get from this is a full encoder of TerraMind. And in that case, it's TerraMind small. Okay, now we have an encoder, we have the data. The question is, what do we do to fine-tune this model, right? And again, all of this, you don't have to take care of it if you just run the config. I'm just explaining to you what happens in the config. So that the moment you want to adapt the config, you want to use TerraTorch yourself, you hopefully have some kind of a better understanding of what's going on under the hood. Perfect. The first thing is we define a callback for the checkpointing. Checkpointing, for everyone who is not familiar with the concept, essentially means we want to save the fine-tuning model okay. We want to save the fine-tuning model weights after every epoch. Okay, so a checkpoint is basically a file that specifies the weights and a couple of other information during a training process. And in that case, we just specify where this should be stored. We also say that we will monitor a specific metric. In that case, it's mean intersection over union. We will always log the best file. So the moment we have surpassed the checkpoint from some of the last epochs based on the current epoch that we are going through, we will replace that so that we don't fill your entire storage with checkpoints, but just really store the best version. And that's also the reason why having validation data is very helpful, right? Because based on that validation data, you can basically see which checkpoint exhibits the best generalization capabilities. In the very beginning of my talk, I said everyone who's familiar with PyTorch Lightning will feel like this is a pretty easy tutorial. Now, what we will connect to is a PyTorch Lightning trainer. And from now on, everything that happens within this trainer is Torch Lightning. This is not TerraTorch anymore. So here, this is the connect between TerraTorch world and Torch Lightning world. So basically, within this trainer, you see that we specify a couple of things, like the precision type. In that case, it's mixed precision, on how many nodes we want to train, for how many epochs we want to train, what kind of a progress bar we want to visualize. In that case, it's a pretty cool one that visually is just easy to digest, where we want to store information related to the training and so on. And then we built the full model. So far, we just built the encoder, right? But now we built the full model. And for building the full model, what we do is we will first specify which task we want to focus on. In our case, that's a semantic segmentation task because we want to segment the extent of floods. And then as a backbone, we will use TerraMind v1 small. Again, we will make sure that the backbone weights are loaded properly by specifying that we want to have a pre-trained backbone. We will use both of the modalities. We will specify our neck, which basically makes the transition between the latent representation we get from the encoder and the decoding dimensions. And then our decoder is, as I said before, a UNet decoder. In a UNet, you typically have to specify the channel dimensions. If there are questions around that, we can answer them separately. But basically, the idea is to have some kind of a hierarchy that's dependent on the dimension in your latent representation of your encoder. We can use dropout, which in some cases make things a bit more stable in downstream applications, a bit more robust. And the number of classes is 2. We specified that before, right? We will use dice loss, which is pretty convenient for this type of downstream applications. You could also use cross entropy loss, but we typically see that dice loss performs really well in this application. As an optimizer, we will use AdamW. It's a best practice in the community, I would say. Learning rates need to be specified, of course. There's another cool tool called TerraTorch Iterate, which allows you to loop over different hyperparameters like learning rates to do hyperparameter tuning very easily. We will not freeze. We will freeze the backbone because in that case we treat it as a feature extractor. Of course, we will not freeze the decoder because otherwise we wouldn't learn anything in this fine-tuning. And then we can specify that we actually want to plot something during the validation, so we get kind of a feeling of the visuals that the model is producing. If we execute this cell, TerraTorch will build the model. We will now also connect a tensor board so that we can monitor our training for a little bit. And then we call the same thing more or less that we called before in the CLI command. Before we said TerraTorch fit and then a config. Now in this case we can say trainer.fit. so trainer.fit on our model and the data module, which will then kickstart the fine-tuning process. You will see that this looks very similar to what we have been seeing before. Before we used a tiny model, now we're using a small model, so we have a little bit of additional parameters. You quickly saw the sanity checking where TerraTorch went through the data loader to make sure everything is consistent and works. And then we will quickly train for 2-3 epochs to then visualize this. So this step will take us 2 minutes roughly. Afterwards, we will load this checkpoint and we will have a look on how the results look after 2 or 3 epochs of training, which is really not a lot. Typically, you would want to fine-tune these models for something between 50 and 100 epochs, which would here maybe take half an hour, something like this. So if there are any questions, then we would have 2 minutes to answer at least 1 or 2 of them.
We have general questions. So while we are waiting, I can start asking you some questions. At this point, I will go to the because they don't refer specifically to these steps, so they are more general one. I will go back to the previous one, and so in case also Johannes and Valerio can answer as you please. There is one question: at what spatial resolution digital elevation model is generated?
The spatial resolution is 10 meters. At the moment, everything that we're doing in TerraMind is at 10-meter resolution, basically. So the DEM that we are generating and the DEM that you can input without any, let's say, domain shift is 10-meter spatial resolution.
Okay, thank you. Second question is also simple. The model has been trained on a dataset that includes both Sentinel-1 and Sentinel-2 imagery?
Yes.
Yes.
Exactly. I think one very important thing to mention here is that Sentinel-1 and Sentinel-2 in some sense can be considered orthogonal modalities. So it's not easy to correlate them. And I think this is something that people should generally keep in mind. If you want to learn the correlations between different data modalities, then if these modalities are completely parallel, there's no real need to learn a correlation between them. If they are orthogonal, then it's very difficult to learn them. So ideally, it's something in the middle, something like a 45-degree angle of similarity.
Okay. Anyway, Sentinel-1 and Sentinel-2 both were considered also at different times. There is not just one time, but
Yes.
can you add also something about the timing? Because this is also interesting, in my opinion.
That's a super important component. Yeah, actually, we are already through this, but let me answer this question. I think it's an important one, and then I will show you what comes out of this 3 epochs of fine tuning. For the temporal component, it's true that TerraMind has been pre-trained on a multi-temporal data set because SSL4EO has 4 time steps, right? It's 1 image per season. It's also true that we don't have a specific temporal encoding in TerraMind. So in that sense, it's not a temporal model. With TerraTorch, we have a temporal wrapper that even for single timestamp models, you can make them multi-temporal by generating embeddings from different time steps and then learning from these embeddings. And with the new results from GeoBench, which just came out a couple of days ago, or maybe they will come out end of this week, I'm not sure, either end of last week or end of this week they will come out. We see that TerraMind outperforms all of the other models, including all of the multi-temporal models with this temporal wrapper. And then as a final side remark, internally we're working on a version where we pre-train TerraMind multi-temporally, and we see that with that, at least in one downstream application that we are using for validation, we can outperform this temporal wrapper. So I would say TerraMind itself is pre-trained multi-temporally in a very naive way, just by feeding it multi-temporal data without telling it about it. We can see that this works a little bit better with novel masking strategies that we are currently developing. And we can also see that just with very simple software tricks like a temporal wrapper, we can outperform other multi-temporal models.
Thank you. And I don't know if there is space for one more question, but I see that it's finished now. So let's go to again to the hands-on, and then we will come back to the questions later.
Perfect. All right, cool. We now have a checkpoint, right? We have weights that are generated after 3 epochs. Don't expect too much from them. It's just 3 epochs, right? But we can test them by just running trainer.test and then the model and the data module. And now we are running over the test file. We will get some accuracies. You will see that the overall accuracy is pretty good because we are largely predicting backgrounds. But even on the water class, our performance is not so terrible given that we just trained for 3 epochs instead of something like 50 or 60. And now we can visualize this and it will look something like what we will see in a second. Too long of a cliffhanger. Okay, so what we see here is in the first column is the input image, like the optical input image. Then the ground truth mask, this is what we would like to get. Then the ground truth mask on that image, and then the predicted mask. And while you can see that this model already really just started with fine-tuning, it's kind of highlighting some areas that are relevant for this task, right? So here you can see that the model gets an idea on where this flood is roughly, even though this is like really unrefined because it's just after 3 epochs, similar for this river and everything related. You see this model is definitely not saturated, but you see that after 3 epochs, it already has a decent idea of where to search for floods. Perfect. Given that we are kind of running out of time-ish for this part of the hands-on, and we want to make sure that you can get your hands dirty in code as well, let me go back to this example of burn scars. So everyone who has some time and wants to look into this, we would be really happy if people participate and give this a try. You go to our repository. We prepared this notebook that I referred to before. There's a collab link. You click on it and you can play around with these 3 to-dos that we added. And I would propose we do a 10 minutes break. We will restart this in a 9 minutes break. So at 3:35 European time, Central European time, we would continue this. And then Benedikt will take over and he will tell you on how to adapt this. And then afterwards, we will answer all of these questions. From my side, thanks a lot for attending this. I'm super excited about all of these questions. It's cool that everyone is interested and you come up with very good questions. There are a couple of questions that should be asked that haven't been asked. So I'm looking forward to answering them in the end. But for now, I would say we take a quick break and we can work on this collab individually.
Thank you, Johannes. And yes, for sure there are other questions, but later. Let us wait for the questions. And as you said, the 10-minute break for the exercise. Okay, thank you.
Should we maybe like everyone gets kind of like a head start and we fill the break with some more questions, or should we wait for the end?
What do you prefer?
It depends on how many questions there are. If there are more than 20 questions,
there are many questions.
Then let's take the break to answer.
If you say the magic word questions, I see appearing new questions. So, okay, I can start with at least 3 old questions of the first part. One of them is, did TerraMind just tokenize the text inputs? For pictures, they are made as patches as input, right?
Yeah, so basically, maybe just a quick 3-line explanation of this process again. So what we want to make sure is that we can learn correlations between different modalities. For image modalities, in principle, you don't need to quantize. You don't need to go to this discrete space of tokens. But if you want to correlate to, for example, sequence data, you need this discrete representation. So while for text modalities, you have tokenizers like BERT that are deterministic. You have a lookup table where you say this word corresponds to this number, this token. We don't have something for images, right? So what we do is in the first step, we learn this quantization, this binarization of a patch into a discrete representation so that the model can learn something like this. Every time I'm seeing the number 4 in Sentinel-1, I'm seeing the number 7 in Sentinel-2. So if I'm now masking the number 7 in Sentinel-2, and I just show the model number 4 in Sentinel-1, I would hope that the model is able to reconstruct that. And even for humans, it's easier to learn correlations like this, right? It's easier for me to correlate to integer numbers than to floating point numbers that are never matching exactly. And it's the same for the model. So the reason why we are quantizing, there are many good reasons, and there are also a couple of bad reasons to do it. But I would say the primary reasons are it helps us to make the training much more stable. It helps us to learn correlations to modalities that we couldn't correlate before. And it has a couple of cool generative aspects that you cannot do if you don't go to quantized space, because if you don't have discrete tokens, you cannot sample from them. Then generating stuff becomes very difficult. Thinking in modalities would not work.
Okay, thank you. Thank you. I hope that is clear. So this was Zhongju Liang asking. We have another question from Harald Christen. It's a bit technical. When will the TerraMind NAPE tokenizer be available?
That's a very nice question.
But we have to explain also what is the TerraMind, the NAPE tokenizer, because it could be that many people don't know.
Yeah. Yeah, it's a fair question, first of all. So NAPE is high resolution data. It's at 1.25 meters. And we are working on integrating that, which means that we have to bridge roughly an order of magnitude in resolution between the other modalities that are available. We have worked on a couple of tokenizers for NAPE already, and we are currently in the step of fusing that into TerraMind. So tokenizing all that data and then starting continuous pre-trainings with that. It depends a lot on how that goes. I think it's a very open question on how to do that best. So we took a lot of time to build the tokenizers, and I think there are still questions around that. I hope that internally we have a first version by the first month of the next year. And then I would say for open sourcing, I cannot really speak on about that because I don't know. Let's say ideally at the end of the first quarter of next year,
Okay.
openly available.
Okay.
But it depends a lot on our experiments. While I was sharing the screen, one of my other tabs was exactly that. So I can keep you updated at the end of this talk.
Okay, okay, thank you. Can we consider one more question? And yeah, and then we leave the other one for the end. So would you share some published examples how different organizations, projects have been deploying TerraMind in their use cases?
I mean, TerraMind is a very open model, right? The license is very permissive, so we are not informed of people using our model directly. But one thing that we do have, for example, is this TerraMind Blue Sky Challenge, where people can submit ideas on how they use TerraMind. So if you go to Hugging Face, there's this Hugging Face demo section, and there's also the Blue Sky Challenge. So you get a couple of ideas there. Another thing, how I try to keep up is seeing who cited TerraMind and what they did with it. For organizations that are deploying it in real life applications, it's very difficult for us to judge actually who's using TerraMind because no one is required to tell us about it, cite us, or give us an indication that it's actually our model that runs under the hood. So there are good things
Yeah.
about permissive licenses and bad things, and I think that's one of the bad things. We cannot really tell just because we don't know ourselves.
Yeah, but this is a pity because you can ask at least to be cited, to be credited in the paper, and in such a way that you can find also how many different applications are available. It's possible to find them, but if there is a credit to TerraMind, it's even simpler. Like it happens, for instance, for some data you are using that you can use them, but just credit acknowledging the providers of the data. You can ask for acknowledging the providers of the software, as a matter of fact.
Yeah, that's a
Can
cool
I
point,
ask you
actually.
the last
Yes.
question? Oh,
Maybe
sorry.
one quick remark on the last question, because it brings up
Yes.
another perspective as well, right? If there's someone on the call who does something cool with TerraMind at the moment and deploys it, let us know as well, because we wouldn't know, right? So if there's any application that we should know about, feel free to let us know. We are also happy to highlight that.
Okay, and I want to ask the last question because I see that the jury is saying Benedikt and Johannes, so it's specifically for you. When I fine-tune TerraMind using a new sensor like Landsat with Sentinel-1, digital elevation model, and coordinates, can you please explain how temporal data is handled, temporal stack of Sentinel-1 and Landsat? Also, when making prediction using the fine-tuned model, can I benefit from the thinking-in-modality method while providing a single modality and a single image? For example, only one Landsat image?
Maybe I take that question because it's very
Yes.
related to TerraTorch. Yeah, so first of all, about like using new modalities, maybe I share my screen for that. Then I can share you. So if you go to the repository, here's the link to the docs, so you can just open the docs. And we have here like a full section about like subset of input bands and new modalities. So there you find like most information about how to use a different modality and so on. So like in general, like in a config file, you can just define like a new modality and this patch embedding. So the first layer is gonna be initialized with random weights if you have like a completely new modality. But you can also do stuff like, for example, if you have a modality which like related to pre-training one. So like let's assume you use like Planet or for Landsat in this example, and you want to reuse the patch embedding from one of the pre-training modalities, you can just include both of them in your like modality name, and the model is gonna like reuse kind of the one from the patch embedding. And then you just have to define the list of bands you want to use. And that's actually something which is related to like this burn scars hands-on session, which you had to do, and which we're gonna do in like 2 minutes. You basically have like all the lists of pre-trained modalities, and then you just have to select the ones you're gonna reuse in your fine-tuned version. So that's how you can combine all of like your different modalities, kind of also if they don't exactly match the pre-training modalities. So that's all handled in TerraTorch, and we try to make it as simple as possible for everyone to use it. If you find something which doesn't work, please reach out, create like an issue. Are we happy to help there? Of course, like, if the time allows it. The second part of the question was about thinking in modalities. For thinking in modalities, it's important to understand that the generation of the intermediate steps is happening with the frozen encoder, because otherwise it's gonna get like very inefficient computationally. So what we basically do is we spend like a tiny bit of computation for this generation, and then the most computation is for like the actual fine-tuning of the encoder. So that's why we keep it frozen. Otherwise, like this model would just take too long for fine-tuning. But that also means that you can only use the pre-trained modalities with thinking modalities. So if you want to use thinking modalities, you have to stick to kind of these ones which you see here. If you have like a new one, like for example, the Landsat modality you mentioned, this is not going to work. I'm very sorry to tell that now, but like at least with the current version of TerraMind, That's basically not possible. I mean, there could be some new ideas, like there are other models like Dofer or Clay who have like this dynamic patch embedding. And you could try to do the same like thinking modalities with them, but like we haven't done that. But at least with our model, you basically have to stick to this pre-training modalities, and only then thinking modality works. And also like in our experiments, we try to like remove some bands, and also basically leads to worse results. So like as soon as your input changes a bit, it's better to just not do it, and to use normal fine-tuning. But if you have like a standard input, like for example, you saw like really good results with like Sentinel-1. So like imagine you have like a downstream task which uses Sentinel-1, and you generate like this LULC map or something as a thinking modality approach. We saw in like some experiments that you get like 5% improvement or something, but then there are rare cases. Like just to be transparent, like don't expect that with every use case, but there are some use cases where this approach can help quite a lot. Often if you have like S1 data, for example, which has like a bit different information content than, for example, Sentinel-2. So yeah, a long answer to make it short, currently not possible with your combination of modalities.
Okay, thank you. Thank you. Very clear, unfortunately, but very clear. Okay. Okay. So I don't know if we want to go back now to our Anson. There are still some questions I will ask in the end. Hopefully we have time to answer all of them. If not, what we can do is to ask our attendees to send to us the questions, and then you will answer offline. Anyway, let us see if there is time. I don't want to steal time. I leave you immediately the floor, Benedikt.
Perfect. Thank you. Okay, then you guys had some times to start with the burn scars example. So I hope you all found the link. I already opened that and installed the setup. So I did the same as Johannes did in the last example. So we have to install it, and now we can import it. And what we have to do is we just have to like adapt mostly like this data processing. So if you want to start with like a new data set, the main part you have to do is basically get this data loading ready. And then the data itself, the model itself, you often can just reuse the setting from some examples, and that's what we're going to do as well. So in this example, we're going to download this burn scars data set. You can also find it in Hugging Face. Let me quickly go to this tab. So this is the data set, was created by Nazar, and has like 6 different bands. So that's like a different modality kind of, like it's still like Sentinel data, but it's differently processed to like this ATLS data with like 30 meter. And they selected like 6 bands of them, which are like most relevant for this task. And we can get some nice statistics about it. Also similar to the last example with the flooding, we have like a positive class, a negative class, and then missing data, which we're going to ignore. And we also have like some data splits here. The thing what they did here is they just provided like a training and validation split. And what we're gonna do is we're gonna reuse another split from like another work, which uses a train validation test split, so that we can actually do like this testing on a different split. Now I'm seeing that I have an error here, which apparently is not resolved. Okay, so apparently probably like I used this one too often. What I'm gonna do is I'm gonna do it locally, but it's also gonna work if you do it in Colab, so that should be the same. So thank you. I'm gonna share my desktop again. Okay, so now I'm switching to my local PyCharm, but it's basically the same as you would do it in Colab. I can maybe also do it a bit bigger. View. Okay, so here I think it should already be downloaded, or I have to import it. So that's gonna take a while. And while we're waiting, we can maybe already look at what we're gonna do here. Here we're gonna use a different generic data module. So like as Johannes shared earlier, you have these generic data modules in TerraTorch, and the idea is a bit you don't have to write the code. You just have to provide a different path, and then it should work. And why we had like this a multimodal module for like the Sentinel Floods 11 example, now we only have like one single modality. So we're just going to use this generic segmentation module because it's just a bit easier to handle. Like you don't have all the dictionaries, but you can just pass the path there. And the beginning is pretty much the same. But for the rest, we should like understand how the data looks like. And now hopefully this should be done. Yes. And here now I have this data path, like my data, and I can also see it here that I have like two folders in here. So again, this looks a bit different than what you can download from Hugging Face, just because we just reshaped the data a bit, but like the data itself is exactly the same. We
Sorry,
can also
Benedikt. Sorry. One question that I believe that is important for the exercise we are doing. There is Andrea De Martis saying, is it possible that the Colab script is not working due to a problem in the data to be downloaded? It says too many download lately.
Yeah, it could be that we like currently accessing it with too many people, but like I tested it like an hour ago before the session, and then it worked. So it could be. I'm gonna check it later, and if it's not gonna work end of today, then we're gonna update that in the notebook. But what you can always do is just downloading the data from Hugging Face. So that's also possible. I think it's just probably like if 1,000 people, like 100 people are accessing this link, it might not work from Google.
Yeah.
Like I
consider that
also
there are under 50 people who are trying to do the exercise at the moment, because I see that we have under 50 live viewers. So yeah.
That's pretty cool. Okay, so like, sorry if you have any issues here. Like, you can always just try it again tomorrow and then rewatch it to check if you did something right or wrong. And like, I hope it's gonna work again tomorrow. And if not, just download the data from Hugging Face. It's also like a two-liner, so it's like a different liner, but like it's also pretty simple to download it there. Yeah. Okay. So now we have the data locally, and we see that we have like the data here and the splits here, and we can check the splits, for example. That's how the split files look like. So we have basically like an ID for every sample, and the data looks like that. So we basically have the data in these merged files, and we see that like these tile IDs are basically path of every sample, and every sample has now like a merged file where all the channels are in there, and then we have this mask file as well. What we can also do, we can just open one of these ones. So this is like now one of the data files. We can open this with like raster.io, and we see that we have like 6 bands, 512 by 512, so exactly what they also describe in this Hugging Face page. And we can also check, for example, the values. So we can see that the values are like all around like 0 to 1. So that also means like for Sentinel-2 data, like you could have like this digital numbers where you have like this range 0 to 10,000, what we use, for example, in TerraMind, or you could have this range, this reflectance range from 0 to 1, which we have now here. So that's actually an information we have to use in a second. okay, so now we have like a bit of understanding of data, and that's basically the first step you always have to do if you want to try a new downstream data set. Now we can use that to like configure this module. And we have to start with like data routes. And we know, okay, like our data route is basically, what was it? Was this one. So we can use this one and just copy it there. And the nice thing is like everything was in the same folder, so we can actually reuse all of that. Then we have the splits. So these are the splits files. Splits. Oh, my PyCharm already does that for me, so that's pretty nice. So we can like do this and test. So now we configured all of that. I currently get some warnings because TerraTorch wants some path files, like this from pathlib path. But let's go try if it works without as well. Then we need to define like some image and label grabs. So what that means is basically we have to tell TerraTorch if you find like a sample with this thing in the name, what is the data and what is the label? And here we know, okay, here's the ID which specifies the sample. Now we have to tell it, okay, that's the label grab and this is the data grab. So we're gonna add that. And now we have to do this one because in between there are some other things which we want to ignore. Here it was merged, so that should work. And then the last thing we have to do is basically we have to standardize the data. And that's something you can do individually for your data set, or you could just reuse the pre-training values from our pre-training. So here I already put like the mean and standard deviation values for S2, L2, A. So that's the modality in pre-training, which is most similar to the HLS data, which we want to use. But these are like 12 values, and we now have to select like which ones we actually want to use in fine-tuning. So we can go back to this description, and we see here basically our 6 values. And then we can also check in the documentation our values here, and we can like they basically match. We need like these 3 values. Then we have this near and narrow, that's like band 8A. And then we have the 2 last ones. So that's the ones we're gonna reuse kind of for our example. So what I'm gonna do is I'm gonna start like new lists, and I'm gonna use like the 3 ones. This is RGB. It's just important that you don't mix up stuff like here. Then we're gonna use this one. These are the last 2, and then 1 in the middle is missing. Now I have to check again. Okay, so from these ones, like 1 house and then this one. So this is not in like S2, L2, A. Okay, so we use this last one, 2, this we skip, and then this should be band 8. And that's something I wouldn't do in a real use case to like do it this risky, but just has to be quick now. Okay, so last 2 ones, and this one should be 8A. So now we have the 6 standardization values. What we notice here is, okay, we have like pretty high numbers here, like 1,000, 2,000 and so on, but our data was only around 0. That's because like this data is in a different scale. So what we have to do is we basically have to scale it by 10,000 to get it into the same scale as the scale we use in pre-training. So what TerraTorch is going to do is basically multiplies all the data with this constant scale and then it applies the standardization. Okay, the rest one, it's the same what we used before. So we basically specify the no data and so on. And then we can run the same as Johannes did, and we can check how many samples we have in validation, and hopefully I did everything right. Let's see. Okay, we have 160 samples, and we can also visualize that. Here I plotted a bit of a helper function. You can also just use the one from validation, which is this one. This does like a min-max scaling, which also works. It just doesn't look so nice. So that's why I just added like this little helper function, which basically just scales to like 2000. And now we should see some examples, but apparently it's a bit slow currently. Now we see them. We can see here now like the image again, the mask, and we can see here in the middle there's a burnt area. Here's a burnt area. This is, for example, like ignored areas where like the probably like the annotators weren't right. Also here, like we have like a none area, and this is also going to be ignored, but we also have this burnt area. We also have like this test set now here, and then we can do the fine tuning. So this is pretty similar to the last example. The only thing we have to do here is we have to tell where we want to store that. So TerraMind burn scores. That's where we're gonna store the checkpoints, and also our default out directory is more or less the same. Then what we have to do is we have to define like some subset of the bands for TerraMind so that the input adapter is correctly. So what we're going to use is we're going to use the S2L2A because that's the modality closest to the HL stator. And then we have to tell which layers we're using. So that's again, we're going to check this long list. We're just going to copy these ones. And then we are like ready to go in a second. So these are the first three ones. Then we have this one. And the last one. Okay, and that's it. The rest of the model is basically the same. So now we can build this one. We see that the model is built. We can probably also check the model. So that's the full task. And this one should be the model itself. I think it's encoder. And then the rest is the same as in the other example. You just fine tune your model. Here, this one, of course, has to check with the one you specified up here. And that's kind of it. So here we see, for example, the full model again. And now we can also see that different to before, we now modified this one. So like you probably don't remember, but like before, like this input channels were like something like 3000 because we used all the 12 bands in the other example. Now we only use this 6 bands, and TerraTorch automatically updated this patch embedding kind of, and then we also have the encoder and the decoder. And now let me start a training just to have like some nice success for finishing this webinar. But that's basically how you adapt your a foundation model to your own data. So I think the most important thing is to understand the data and to like adjust everything in the settings. And then the model itself is pretty simple as long as that the modalities basically match. And if you have like issues there, it's like most of the time it's because something here is not correct. And now it's training. So that's all from my side on adapting the model to burn scores. Unfortunately, we didn't have the time to see the predictions, but they're probably equally bad because we also just trained for 2 minutes. So it's going to be similar to the examples Johannes showed. And I just saw like we currently have an issue with like some macOS fine-tuning versions. So it's based on macOS, so on like Colab, you shouldn't get this issue. And there's also an easy fix. There's an issue I created in TerraTorch with how you can fix it. It's like one line which is missing. But it's basically just locally if you run on macOS. Okay, that's it from my side. Do you have any more questions, Maria?
Yes, there are many questions, so be prepared. So, Roman Tufik, could you suggest a small size, high quality public data set to practice the fine tune? Anything from agriculture, ecology, land classification, it would be really good.
Yeah, so I think like our standard data sets, which we show is always like sum of floods, 11 burn scars. So it's definitely good to just experiment with them. They're like pretty good in terms of like size and annotation quality and so on. We also have like another example with a multi-temporal crop data set. So it's also on the TerraMind repository. You can click through this notebook as well if you're interested in multi-temporal tasks. So it's like basically just 2 lines you have to modify, and then you turn TerraMind into a multi-temporal model with this temporal wrapper. So that's pretty simple. And regarding like other data sets, you can check out like GeoBench, Pangaea. As Johannes mentioned, GeoBench 2 is going to be out in maybe it's already out, maybe in some days. And just check like which data sets fits to your use case or you're interested in. And they're normally not like super big, so you can also work with them quickly.
Okay, thank you. Thank you. So, one person who wanted to practice, there are some examples already available. Just to understand that if you are able of working in a correct way with TerraMind, that is very good. Luckily, I see there is one new question. Anyway, let's go ahead. Are there any plans for attention time pooling for the temporal wrapper on TerraTorch?
So the temporal wrapper is meant as like a idea independent of the backbone. So it basically just wraps the backbone and turns it into like a mid-fusion temporal model. So you can use it with like a VIT backbone with any foundation model and so on. So we don't think that we're gonna like modify the encoding in any way in this temporal wrapper. But we do work on like some temporal understanding, which is a bit improved for TerraMind. So you can definitely stay tuned for the next version. It's gonna have like some more features, and you don't need the temporal wrapper anymore.
Okay. Then I want to say just something about TerraTorch because as we know that not all the people are familiar with TerraTorch, with Andrea, we were thinking of organizing, and we are already organizing also a small workshop about TerraTorch to present it in such a way that the people who are not so fluent in TerraTorch, they can learn something more. It will be in February, if I'm not wrong, this webinar. So if you are patient and you are not good in TerraTorch, you can wait February and you will become very, very good in working with TerraTorch. Anyway, let's go ahead with another question. The question is if it is possible to practice fine-tuning in Google Colab. And Roman Tufik says that he always have a problem of maximum file uploaded there. And of course, also the problem with maximum RAM allocation for Colab free version. He wants to practice different type of PEFT in that model, and he needs your advice.
Yeah. So Colab, I think it's pretty nice to like experiment a bit, having like these workshops where you just have like a lot of people and they just need like a small GPU to run it. I don't think it's like the best platform if you actually want to do like real experiments and so on. So like I wouldn't recommend it for like everyday usage. So maybe with Colab Pro, it's fine. But often like if you want to do like benchmarking experiments and so on, you probably want to have like a local or GPU or a cluster where you can run your things. Yeah.
Maybe one thing to add there. One reason why we released TerraMind Tiny and TerraMind Small is that people can use them on their local machines depending on the machine. Like for example, if you are a MacBook user and you have MPS, then fine-tuning a tiny model should not take more than an hour or so. It will not give you the best performance, but just to get things running, make the experiments once, get some understanding, and then scale it up on a GPU that you might want to rent somewhere on a like cloud providing platform, or have some university cluster or other academic cluster. I think that's hopefully that's our intention, at least with these models, like small and tiny. I think small is a pretty good trade-off between the computational effort and the accuracy that you get out of that. And let's say if small is working, you can expect that base is obviously working somewhat better. But I would say I would be surprised if the general findings would be different from your experiments on small compared to base. So maybe that's another angle. Start with the tiny and the small.
And let us hope to go toward more sustainable solutions in such a way that really everyone can use them. This is the tendency. Obviously, we are still in the beginning, but one relevant point is to consider this aspect also of usability by people who don't have so big capacity in their computer or what they have available. So, but again, you say that you are considering this point of view and try to keep in mind also to have solutions for these cases. Okay. So, George Scott, suppose I want to use TerraMind, but with a custom acquisition, for example, multispectral imagery from a tasked satellite. Similar to Jury's question, how do I bring that in for inference? And do I need to downscale to modify the resolution to match Sentinel?
So the question is like, if you want to fine-tune TerraMind for this type of satellite. So that's definitely possible. Like you have like a data set aligned with samples with the satellite. You can just use it as we did with the HLS theta. You can just specify a different modality. Also, if you have like a different resolution, like the model can definitely pick that up and fine-tuning. Like we saw that, like even with high-res data, it's not gonna be like perfect, but it's still gonna work. And it's definitely not worth like downscaling into 10 meter or something, because then you lose a lot of information. Like the information content is much more important than the model being pre-trained on that. If your question is specifically to can I use a fine-tuned model which was fine-tuned on a different satellite on this new satellite, that's gonna be hard. Like that's something you have to test to see if the model can basically generalize. If it's the same channels, then maybe. Then it really just depends on like how big the domain shift is between the satellite you're using for like fine-tuning your model and the task satellite you want to run inference on. But ideally, if you want to have like good performance, I would always try to fine-tune a model also on this satellite you want to run inference on, even if it's just like a few samples and just do continuous pre-training, like to train your task for like flooding on like Sentinel-2, and then have like, I don't know, 20 samples, just do continuous fine-tuning with like this task satellite you're interested in. But that would boost your performance quite a lot compared to just running zero-shot inference.
Okay, thank you. So another question. When fine-tuning TerraMind with Landsat, can the fine-tuned model during prediction benefit from the other modalities like the digital elevation model Sentinel-1 if it was included during fine-tuning but not used during prediction? Jury wants to use Landsat.
Yeah, that's fine.
It's clear. It's clear. Now we understood.
So my understanding, how I understood the question, and please correct me if I'm wrong, but like you want to fine-tune it with like several modalities, including some that you don't want to use in inference. Actually, we haven't tested that. I don't know. Like you definitely do it. Like the model is not gonna fail or something. Like TerraTorch basically supports this like flexibility. What you can do is in TerraTorch itself with TerraMind, there is like this modality drop rate is a parameter you can set. So for example, you could pass it as modality drop rate 0.1 or something. What it basically does, it basically randomly drops 10% of the modalities during fine-tuning. And then the model basically learns to be more robust against missing modalities. So if you do that, it might be that the model performs even better in inference if you provide these additional modalities in fine-tuning. But I haven't tested it, so I can't promise anything.
Yeah, it's a
Yeah.
very unique setup. I agree on that, but it's an exciting question. One thing from my side, I think it's important to consider the VIT backbones of TerraMind in the multimodal sense as it's a network that reserves individual partitions, like not explicitly but implicitly for individual modalities. So the moment that you fine-tune with more modalities and during inference run with only one, I would be surprised if there's enough activation in the model to kind of compensate for the missing input. So what I'm trying to say is, given that these models typically reserve individual partitions of the model weights for individual modalities, not having them present during prediction is probably harming the performance.
Yeah. The other general question for me is speaking about Landsat is that is not completely clear to me why you, jury, but this is a question for you, but you are not answering, but why you want to fine-tune TerraMind with Landsat, which is worse in resolution. This is not is something that I don't understand. But okay, there can be good reasons. You have good reasons probably for doing that. Let's go to the next one. Are there any plans for attention type pooling for temporal steps? Is that something you have looked into? Luc Vermeer.
I think we already have this question, right? Like I
Yeah.
think I saw in the chat that Luke had some issues with sending the questions, so maybe it came up like twice.
Yeah. Alessandro Variale, how many datasets are available? Is there a catalog? Datasets are available is not completely clear, this question, if are the dataset used for training or
So
Go ahead.
okay. So the data set for pre-training is like TerraMesh that's available on Hugging Face. You can just download it. You just need like 17 terabytes of storage. If you want to pre-train your own foundation model, feel free to do that. That's why we published it. For downstream tasks, I already mentioned like these benchmarks, which are already like a good source for different tasks. You can also just check out Torch Geo. So Torch Geo has like a huge list of data sets for different downstream tasks. And Torch Geo data modules are completely integrated into TerraTorch. So TerraTorch is reusing a lot of things from Torch Geo. And Torch Geo has like really like a large collection of data sets, and you can kind of reuse this code directly in TerraTorch and fine-tune TerraMind with it. So that's also like a good idea to look for data sets if you're interested in different downstream tasks.
Okay, so a message to Paulina, we are not accepting other questions because we are definitely late. So I will just ask the questions that are available now, but then for next questions, people have to write to us if they want to be answered. So Mohammed Buritz, does TerraTorch provide a method for assessing the learned embeddings?
Yeah, so we have like this new functionality of generating embeddings and testing that. So that's something Isabel Wittmann is working on, a colleague of ours, and she's actually running this February webinar also around these embedding generations and so on. So you can definitely check out TerraTorch for these examples and also the next webinar for getting more insights into like embedding generations and testings and so on.
Yes, yes, very good. So another question for the Sentinel-2 data, where the Sentinel-2 data were 2060 meter spectral bands interpolated to, no, the question is, if the 20 and 60 meter spectral bands were interpolated to 10 meter resolution, and if so, would we also need to apply this same process to our own Sentinel data when fine-tuning? Also, do you have an idea of what a reasonable size label dataset for fine-tuning would be? I realize it will vary between tasks, but just an idea from these example datasets.
Yeah. So yes, we resampled all the bands to 10 meters. For all the satellites, like Sentinel-2, we basically used nearest resampling, so we didn't interpolated any data to like don't get like any like unreasonable values or something. So that's just nearest interpolation for 60 and 20 meter bands. And for them, we used like this linear interpolation to not have like sharp edges in the elevation. And yeah, if you want to fine tune any modality with TerraMind, it basically has to be single resolution. It can be multimodal, but all need to have like the same resolution. So that's the important thing to consider currently. It doesn't have to be 10 meters. It can also be like 30 meters, 1 meter. The model can like learn these new resolutions and fine tuning. But it does have to be one resolution across all modalities in your tasks. Yes, that's the main question, right? Did I forget anything?
Okay.
And
Now the second
size,
one is the size of fine-tuning.
right? That's as she pointed out, or he put it on. I'm not sure who asked the question, but I think it's true that it varies a lot. But for most of the downstream applications that are in segmentation world, and it's something binary or few classes, I would say a couple of hundred instances are generally enough for most of the settings. So if that would not be working at all, then I think it might more be related to how the model is configured or something like this. Yeah.
So for your experience, couple of hundred is reasonable.
For
At
example,
least
one flats 11
we can
and
start in this way.
yeah, exactly. For Sen 1 flats 11, it's 252 samples, and you get an IOU in water class segmentation of over 90% across models. Again, it varies a lot, but I would say everything that's in the hundreds should be a good starting point. It should not be in tens.
Yeah, yeah, definitely. 10 is not enough. So let us start with 100, which can be a reasonable number. Okay, the last question that I accepted is by Marcel Matteo. Is the code block the same for all modalities, or is it learned separately for each modality? That is very technical.
I'm not sure I understand what's meant with code block.
I think the different parts of the model. So the patch embedding is separately for every modality. So the patch embedding is this first linear layer which translates this pixel map or like pixel patch into like this one token embedding. So that's per modality. That's why you have to specify that in the config file, because then TerraTorch knows which one to load. But the transformer blocks, which basically follow, they're like all shared between the modalities. So basically they all have some understanding of all the different modalities, and the model figures it out then itself how to like prioritize it and so on, and how they interact.
Essentially, what the encoder has to learn in the transformer blocks is just to mix these different modalities and learn how they interact with each other, but not more than that. Just create a shared representation of all of them. So that's why everything is integrated in a single encoder.
Okay, thank you. So thank you so much. I believe that you answered a lot of questions. I have to say that probably this webinar got the record about the questions that were asked by the floor. And we had also a good number of the attendees because there were under 50 attendees. So let us hope that we met the expectations. I want to thank you also, Valerio, who is, I don't know if Valerio is still here with us. Yes, Valerio is still here with us. Thank you so much. I learned a lot, and I believe that now the point is for people to start playing with TerraMind and building something good. If you have relevant examples, please let us know, because we are interested also in knowing, having your feedback about these workshops the people here are kindly offering. So thank you so much, Johannes, Benedikt, and Valerio. And I give the floor back to Andrea for the next events. Thank you.
Thank you very much, Maria, for moderating this event, and of course, also from my side, thank you very much to Valerio, Benedikt, and Johannes for this great session. Very didactic workshop, very well organized. Also from my side, I want to thank all the participants for being here. I was really impressed by the level of interest this workshop generated. We had to extend 20 minutes the session to answer all the questions. So the workshop material will be available from the neural network, and of course you can also watch the recording on YouTube and neural network. I want to remind, as Maria was saying, the next planned workshop for the GUI workshop next year. Maria already mentioned the workshop on TerraTorch that will be on 19th of March, but before we'll have 3 other workshops. On January 14, workshop from Google on the Alpha Earth foundation model. Then 2nd of February, we will have the University of Cambridge, which organize a hands-on Tessera time series embeddings for geospatial analysis. And then also 25 of February, IBM Research Europe and the German Aerospace Center will have another event on the embedding workflows for Earth observation tasks. So stay tuned for those exciting developments in GI, in geospatial foundation models. And I thank all of you again for your participation. And with this, let me give back the floor to Anna. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.